So, earlier, I said that the sun shines and produces energy because of nuclear fusion in its core. But then I just kind of glossed over that and kept on going. I'm going to circle back to it now. Why is it that nuclear fusion produces energy? How does that work? That's what we're going to talk about. So nuclear fusion, in case you don't know, is when you have two atoms, or more, two or more atoms, and you take their nuclei and you push them together and make a new atom out of the two or more previous atoms. So here's something kind of interesting. We all have our concept of atoms, right, where we have the nucleus in the middle with the electrons going around the nucleus, right? And the nucleus has protons and neutrons in it. Well, what kind of funny, strange quality about protons and neutrons is that their masses are actually kind of affected by the sort of nucleus that they're in. Their situation, the sort of interactions that they have with other protons and neutrons in their nucleus can change how massive they are slightly, which can lead to some pretty strange things happening. Now, nuclear fusion, I should say, it's a very general term. There are lots of different kinds of nuclear fusion that you can do with lots of different kinds of atoms. But I'm going to go with one simple and highly relevant example for this class, which is the fusion of, I want to use my red marker, the fusion of 4 hydrogen atoms. These are each one proton. A hydrogen atom is one proton, usually one proton with one electron going around it. But if you have just a proton by itself, then you can think of that as a hydrogen atom that has lost its electron. So these are 4 hydrogen atoms with no electrons, and they can fuse into one helium atom. The helium atom being an atom with 2 protons and 2 neutrons in its nucleus. But here's the funny thing about this. Due to what I was talking about earlier about the masses of protons and neutrons being variable, there's a difference in the mass between these two things. Now, protons and neutrons are a little bit more massive, but they're very close. So it is really weird that the helium atom is like about, if I recall correctly, 0.8% less massive than the 4 hydrogen atoms put together. So the reason it's 0.8% less massive, like I said, is because the situation in this nucleus affects their mass some, but where did that 0.8% of the mass go? Did it just disappear? Well, no. Here's another equation. Well, not another equation. Here's an equation that I imagine many of you are familiar with. E equals mc squared. Einstein came up with it. One of his insights was that energy and mass were interchangeable, right? You could convert one into the other and back. And he derived E equals mc squared as an equation which sort of describes the exchange rate between mass and energy. For instance, let's say I have 2 units of mass. And I want to know how much energy I would get if I turned all that mass into energy. Well, I would plug in 2 here for the m, the mass, E is the energy, and c is the speed of light. So I would multiply my 2 times the speed of light times the speed of light again, because it's the speed of light squared, and I'd get the amount of energy that I would get. Now here's the deal. The speed of light is very fast. It's a very big number. I believe it is about 299 million meters per second. Every second, light in a vacuum moves 299 million meters. That's fast, right? So, you can see how this is a very favorable exchange rate. Even a small amount of mass turned into energy can give you a lot of energy. And in the core of the sun, this kind of situation is happening all the time. Where did the 0.8% of the mass go? It gets turned into energy, according to E equals mc squared. And in the sun, this kind of reaction is happening all the time. Constantly, many, many times, at all times. And even though it is such a small amount, with this huge exchange rate from mass to energy, and thus rate at which this kind of reaction is happening, that provides enough energy for the sun to shine. It provides the energy for the sun to do what it does. Alright, so, let me think. What am I going to do now? Alright, so, with that, I think I'm going to finish up this video, and I'm going to, in the next video, talk about the specific process by which the sun takes 4 hydrogen atoms and fuses them into 1 helium atom.